Hello, today we're going to be discussing current part 1 and we're starting with these current chapters. There are 3 current chapters which are divided into current electricity, which is what we're starting. Then you have household circuits. Then you have electromagnetism. Okay, now out of this, household circuits is a small chapter and it is mainly just theory. Now, current electricity and electromagnetism, I'd say these are two of the toughest chapters in the entire syllabus, okay? Because both of them require a very deep understanding of the concepts. So, both of these you'll see they'll have theory. There is a lot of theory, but this is not theory which has to be memorized or theory which will be tested. This is theory which you have to understand. They're not going to test the theory at all. They're not going to test the theory, yet you need to know every single part of it, because application of the theory comes quite a bit, and if you don't know the concepts behind the theory, then you will not be able to answer the questions. Aside from that, you also have numericals. I believe you will get numericals from current electricity. Electromagnetism, there shouldn't be any numericals. Usually, as per what I've seen, you will get a 4 marker from electromagnetism, and you will probably get a 4 marker from current electricity as well. Okay, so electromagnetism, usually they base it of a very important concept, two very important concepts, which is, I mean, you know what, we'll discuss that when we talk about electromagnetism chapter. In current electricity, the toughest questions which they give, I think, are questions where they'll provide a circuit and then they'll ask numerical questions based on the circuit. There isn't much of theory which can be questioned for current electricity. This is going to be more numerical based. But today we are going to talk about current electricity part A, which talks about charge, current, potential difference, resistance, and Ohm's law. It is the longest part of this chapter, and it is unfortunately the one with a lot of theory. Okay, part A is going to be just filled with theory. This part of the chapter is filled with theory, but you need to understand all of it so that we can move on to the numerical parts, because if you don't really understand this, you won't be able to apply it for the numericals. Okay, so let's start with charge. Okay, in 9th you guys have studied that if there are two bodies, okay, these are two different bodies. Now if you bring them together and you rub them, one will get a positive charge, one will get a negative charge. Okay, the one which gets a positive charge is the one which gives electrons, right? And the one which gets a negative charge is the one that receives electrons. So what we can conclude is that charge itself is a result of transfer of electrons. Okay, so charge is solely dependent on the transfer of electrons, but this is only in this case where you rub two non-conducting bodies together, right? Now what we also learned in 9th grade is that two positively charged bodies will repel each other, and two unlike charges will attract each other. Okay, very simple concept. Now we're going to move this a bit further. Like we discussed, charge is the product of transfer of electrons, but now we'll move on to saying that charge is caused by either an excess or deficit of electrons. Okay, so now if a body is neutral, okay, if a body is neutral, it has no charge at the moment. Now what happens is, if it gives electrons, which means it has a deficit of electrons, like we discussed, which is what happens when you give electrons, you'll get a positive charge. So now again, it's completely stable right now. So the charge of this is 0. So when you take electrons out from this, it gains a positive charge. When you give this electrons, it gets a negative charge. And basically this happens because electrons are negatively charged bodies. So obviously from a neutral body, if you remove electrons, which means you're removing the negative charge, that means it will now have a positive charge. And if you're giving it more electrons, you're giving it more negative charge, then it's going to have a negative charge. Okay, so now we've discussed that charge is just dependent on electrons, excess or deficit, right? So how would you actually calculate what the charge of a body is, right? Now the charge is basically the number is based on the number of electrons, okay, number of electrons that are in excess or in deficit, right? So if a body is negatively charged, we know it has excess of electrons. How many electrons? That is your charge, right? That is what your charge is. Or if it has a positive charge, which means it's in a deficit of electrons, how many electrons does it require to become neutral again, or how many electrons has it lost to make it in a deficit, right? So because it's always dependent on electrons, we know that the charge of a body will always be a certain number n multiplied by the charge of electrons, right? Certain number n here we will take as the number of electrons in excess or deficit multiplied by the charge of one electron. So we represent charge as Q, and numerically this charge will always be equal to the number of electrons in excess or deficit multiplied by the charge of one electron. Now we know that charge can be positive or negative, so we'll put a plus minus here, right? Now what exactly is the charge of one electron? The charge of one electron is minus 1.6 into 10 to the power minus 19 coulomb. Okay, coulomb is the SI unit of charge. This is how you spell it, coulomb. Okay, COULOMB, coulomb. So the charge of one electron is minus 1.6 into 10 to the power minus 19 coulomb. So now, simple question, if I say that 5 electrons, a conductor, is in excess of 5 electrons. Okay, what is the charge? Okay, simply we know that Q is equal to Ne. Okay, so N over here is 5. We can simply say Q is equal to 5 into minus 1.6 into 10 to the power minus 19 coulomb. Okay, so Q is equal to minus 8 into 10 to the power minus 19 coulomb. But what if instead of excess I said deficit? You would apply the same formula. Q is equal to 5 into minus 1.6 into 10 to the power minus 19, which is equal to minus 8 into 10 to the power minus 19, and say yes, this is the charge. But since it is in deficit, always remember to put a positive sign. Okay, don't make any mistakes here. So how does a charge in a body actually work? Okay, let's take two examples. Okay, if you have a body which isn't a conductor, like wood, okay, if this is a piece of wood, there'll be certain points around the wood where maybe there are a few electrons in excess, and here this is where it'll have a minus charge, right? But the only thing is, say that these are other positive particles, there are some electrons here, electrons here, electrons here. So we'll say that the charge of wood resides in this region where there is an excess of electrons. But the difference between this and a metallic conductor like copper, okay, if I take copper, what you'll notice is that you'll notice a similar thing. There'll be electrons, there'll be positive particles, okay. Only difference is the electrons in wood, they cannot move. They are fixed at their positions, they are not free to move. So wood is a non-conductor or insulator because these electrons cannot move. But in copper, these electrons are called free electrons because they can move around, and this makes copper a conductor. Mostly all metals will have free electrons, and that is why they can conduct electricity. To understand this further, let's move on to current. Current is simply a charge in motion. Okay, if I have a body which is negatively charged and it starts moving, I'll say that this constitutes current. This is basically what current is. If a charge is moving, that's current. Now, more specifically, current is the rate of flow of charge. Okay, whenever something is called rate, it means that you're dividing it by time. You're dividing it by a certain amount of time, like velocity, or let's acceleration A is equal to rate of change of velocity. So we divide change in velocity by time, right? Because it's rate of change of velocity, so it's change of velocity divided by time. Okay, so here we have the rate of flow of charge. So we're going to take charge and divide it by time, and current is represented by I, So we can say I is equal to Q upon T, where Q is charge and T is time. But how does this make sense? If we put everything together, we'll say that if a charge Q flows through a conductor in time t, then it constitutes a current I. Okay, so if a charge Q flows through a conductor in time t, then it constitutes a current I. Okay, now let me ask a small question. If I ask you okay, before this, SI unit of current will be SI unit of charge, which is coulomb, upon SI unit of time, which is second. So we can say C upon second, right? And this is what we call ampere. Okay, so the SI unit of current is represented by A and it is called ampere. Simple. So now we know that 1 ampere of current will flow through the conductor. 1 ampere of current will be said to flow through this conductor if 1 coulomb of charge flows through the conductor in 1 second. Okay, so if this charge is 1 coulomb, this time is 1 second, then we will get the current as 1 ampere. So now similarly, let me ask a question. A current of 5 ampere flows through a conductor in time of 10 seconds. How many electrons flow through the conductor in this time? Okay, so a current of 5 ampere flows through a conductor in 10 seconds. So how many electrons will flow through the conductor in this time? So let's plug these values into our formula. I is equal to Q upon T. Here current is 5 ampere, so 5 is equal to Q, which we don't know the charge at the moment, upon time 10 seconds. Okay, we can take 10 here to the left side and say that Q is equal to 50. But now how do we get the number of electrons? We know that Q is equal to N into the charge of an electron, right? So we can Q is equal to N, which is the number of electrons in deficit or in excess, into the charge of 1 electron. So here Ne is equal to 50. We know that E, the charge of 1 electron, is equal to 1.6 into 10 to the power minus 19 coulomb. Here it doesn't matter, the negative and positive doesn't matter. since we've just asked for the number of electrons that are flowing, and a number will always be positive. You can't have a negative number of electrons flowing, right? So here this is equal to 50, so n is equal to 50 upon 1.6 into 10 to the power minus 19 coulomb. Okay, remove the coulomb right now, you don't need it for the calculations. So 50 upon 1.6 into 10 to the power minus 19 is our answer, right? Now, okay, let me go back, let me erase some of this. Okay, so this was a simple question based on this formula. It's taking so much time. Okay, now let's see. Current is a scalar quantity. Okay, current is a scalar quantity, which means it has magnitude, but it does not have direction. Okay, does not have direction. Now this is because the direction of current is conventionally taken as the direction opposite to the flow of electrons. Okay, so let's look at a small example. I have a body. Okay, this body has 1 2 3 4 electrons in excess, and there's another body which has 2 electrons in excess. So now if you look at it comparatively, this one has a more positive charge, or I should say this one, since it has 4 electrons in excess, this will have a more negative charge, right? Because this will be 4e, this will be 2e, right? So this has more negative charge, this has more positive charge. So what we're going to see here is, if these two are connected, okay, if these two are connected by a conductor, if these two are connected by a conductor, the electrons will start to move in this direction. See, because this has a more positive charge, this has a more negative charge, right? Electrons are attracted to more positive charge, right? Because electrons are negatively charged, opposite charges attract each other, so the electrons will start to move towards the more positive charge, है ना? Electrons will start moving towards the more negative positive charge. But now we say that current, which is I, moves in this direction. So if electrons are flowing in this direction, then current will flow in the opposite direction. And even if we switch it, if the electrons are moving towards the left, we'll say that the current moves towards the right. That is the direction of current, and it is a scalar quantity because this is always how the direction is, right? Now we move on to potential. Okay, this is going to take a little bit of explaining and a lot of understanding, right? Let's say we have two charged bodies. Okay, one is positively charged and the other is also positively charged. Now I want to bring this positive charge close to this positive charge. I want to bring these together. What will happen? As soon as I try to bring these together, this will create a repulsive force. It will repel this positive charge, क्योंकि हमें पता है कि like charges तो repel करते हैं. तो जब ये इसके पास में जाएगा ये इसको रिपेल करने लग जाएगा. सो इफ़ आई वॉन्ट टू ब्रिंग देम टुगेदर, अगर मुझे दोनों को बिल्कुल पास में लाना है तो मुझे अपने तरफ से कुछ वर्क लगाना पड़ेगा, मुझे फोर्स लगाना पड़ेगा और वर्क करना पड़ेगा ताकि ये दोनों एक साथ आ जाएं. ये जो रिपल्सिव फोर्स है, इसको ओवरकम करने के लिए मुझे इस पर और दबाव लगाना पड़ेगा. आई विल हैव टू पुश दिस मोर, आई विल हैव टू अप्लाई वर्क so that these two eventually come closer. Okay, now if I have a positive charge and I have a negative charge, मैं नोटिस करूँगा कि ये दोनों will eventually come closer. These two will eventually come closer. और ये इसलिए होता है because they will be attracted to one another. ये एक दूसरे से अट्रैक्ट होंगे बिकॉज दीज आर ऑपोजिट चार्जेस, है ना. सो दे विल गो क्लोजर एंड क्लोजर टू ईच अदर. वो बिल्कुल पास में आ जाएंगे, लेकिन इनको पास में लाने के लिए इन चार्जेस ने वर्क करा होगा, क्योंकि वर्क करने के बिना ये तो पास नहीं जा सकते. सो इन दिस केस वी आर अप्लाइंग वर्क. We are doing work, and in this case the charged particles are doing work. Okay, लेकिन कॉमन चीज़ देखेंगे, वर्क इज़ ऑलवेज देयर. सो अगर दो चार्जेस को पास में लाना पड़ेगा तो वर्क होएगा ही होगा, वर्क होगा. Work will definitely happen whether we are doing it or the charged particles are doing it. Work will take place. Okay, so now if I want to bring a lot of charges together, let's say I want to bring 5 positive charges together, then put one negative charge here, one negative charge here, one positive, one negative, one positive, like this. I want to create an entire region of charges, right? This will require a lot of work. या तो मैं करूँ या पार्टिकल्स करें, वर्क तो लगेगा ही इसमें इतनी सारी चार्जेस को पास में लाने के लिए. नाउ व्हाट एग्जैक्टली इज पोटेंशियल? पोटेंशियल इज द अमाउंट ऑफ वर्क डन इन ब्रिंगिंग द चार्जेस टुगेदर. ठीक है, अब ये चार्जेस को जो मैंने इकट्ठा किया है, इनको एक साथ लाने में द वर्क डन, वही होगा पोटेंशियल. ओके, नाउ द डेफिनेशन ऑफ पोटेंशियल इज बेसिकली द वर्क डन in moving a positive test charge from infinity to a point. The work done in moving a positive test charge from infinity to a point per the charge of the particle इसके लिए the charge of this per the charge of this is the potential at that point. ठीक है, ये सेम है, these two points are the same. So let's break this down. The work done, क्योंकि हमें पता है कि वर्क तो होता ही है ना, in moving a positive test charge, a positive test charge, this is basically a positive charge, लेकिन ये बहुत बहुत कम चार्ज होता है इसमें. It has a very small charge. Okay, now we are going to be moving this from infinity to a certain point. Okay, so now जैसे मैंने यहाँ पे बनाया है, I have a region of charges. ठीक है, ये ऐसे ऐसे नेगेटिव पॉजिटिव, ठीक है. लेकिन अब मैं क्या कर सकता हूँ, इवेंचुअली आई विल रिप्लेस दिस विथ, आई कैन से दैट दिस इज़ अ सिंगल बॉडी, ठीक है, और इसमें कुछ ओवरऑल चार्ज होगा. लेट्स से ओवरऑल पॉजिटिव चार्ज है ना. अब हमने क्या लिया, एक पॉजिटिव टेस्ट चार्ज, छोटा सा, बहुत छोटा सा एक पॉजिटिव टेस्ट चार्ज लिया हमने, है ना. अब हमें पता है कि ये जो पॉजिटिव चार्ज है, दिस विल रिपेल दिस अदर पॉजिटिव चार्ज, है ना. ये तो एक दूसरे को दूर करते रहेंगे. लेकिन अगर हम कहें, इफ़ वी से दैट द डिस्टेंस बिटवीन देम इज़ इन्फिनिटी, इनमें इन्फिनिटी की डिस्टेंस है, सो ये इसको और रिपेल कर ही नहीं सकता, ये इसको और रिपेल ही नहीं कर सकता, तो पहले से इन्फिनिटी डिस्टेंस में है ना. सो राइट नाउ द फोर्स अप्लाइड बाय दिस बॉडी ऑन दिस बॉडी, द रिपल्सिव फोर्स इज ज़ीरो. अभी ज़ीरो है फोर्सेस, अभी कुछ फोर्स नहीं लग रही. बोथ ऑफ देम आर जस्ट देयर एट अ सेपरेशन ऑफ इन्फिनिटी. लेकिन हमने क्या बोला, अब हमें इस चार्ज को एक पॉइंट P तक लाना है, एक पॉइंट P तक लाना है हमें, विच इज़ इन द विसिनिटी ऑफ दिस चार्ज. ठीक है, मतलब ये जो ये वाला चार्ज है, बड़ा वाला, ये इसके सराउंडिंग्स में है और ये इस चार्ज बॉडी से अफेक्ट होगा. ओके, तो अभी इस पर कोई फोर्स नहीं लग रही, लेकिन जैसे ही हम इसको आगे बढ़ाते रहें, जैसे वी स्टार्ट मूविंग दिस फॉरवर्ड, है ना, एज वी मूव दिस फॉरवर्ड, ये अब इन्फिनिटी तो नहीं रही, इनके बीच का सेपरेशन तो कम हो गया, तो अब ये चार्ज बॉडी इसको रिपेल करती रहेगी, रिपेल करेगी, तो हमें और वर्क करना पड़ेगा ताकि ये इसके पास आ जाए. अब हम क्या करना चाहते हैं, वी आर ट्राइंग टू फाइंड आउट द पोटेंशियल ऑफ दिस पॉइंट P, potential of point P. Okay, so potential of point P will be the work done by this charge if this charge is Q. ठीक है, इस चार्ज को इस पॉइंट P तक लाने में, इस बड़े चार्ज के प्रेजेंस में जितना भी वर्क W लगा, द वर्क W डन, ताकि ये इस पॉइंट तक पहुंच जाए, ठीक है, अपॉन दिस चार्ज. ठीक है, तो W अपॉन Q, दिस इज गोइंग टू बी द पोटेंशियल ऑफ पॉइंट, दिस इज द पोटेंशियल ऑफ पॉइंट P. ओके, ठीक है. इस पे उतना क्वेश्चन आई डोंट थिंक इस पे आएगा, बट इट विल नॉट हार्म यू टू अंडरस्टैंड इट. ठीक है, नॉर्मली आई डोंट थिंक दे इवन टीच एग्जैक्टली हाउ पोटेंशियल इज कैलकुलेटेड, एंड दे डोंट टीच एग्जैक्टली व्हाट द concept is, but it's good to know. Okay, so now we can say that potential at a point is defined as the work done per unit charge. Instead of positive test charge per charge of the particle, you can just say the work done per unit charge. ठीक है, so this is basically what potential is, है ना. अब we will look at the SI unit of potential. So SI unit of potential will be SI unit of work, which is joule, upon SI unit of charge, which is coulomb. So this is going to be joule per coulomb, or JC minus 1, or JC माइनस वन, और इसको हम मानते हैं एज V और वोल्ट्स, ठीक है। वोल्ट 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 represented by V, and this is the equivalent of joules per coulomb, or JC minus 1. Formula is potential at point P. Potential at point P is work done in bringing a positive test charge from infinity to that point P per the value of the test charge, ठीक है। सिंपल सिंपल। सो नाउ इसको थोड़ा और आगे बढ़ाएंगे टू पोटेंशियल डिफरेंस, ठीक है। नाउ नॉर्मली we'll be considering circuits wherein we'll have a point A, point B, and current will flow through these 2 points AB. We won't consider them individually. So for our calculations, it is easier to find out the potential difference, or PD, between A and B, rather than finding out the potential of A and the potential of B. It will be easier to just find the potential difference between A and B, because our current is only going to flow within these 2 points A and B, right? So now the potential difference over here will be equal to the work done per unit charge, ठीक है, in moving a positive test charge from point A to point B, ठीक है, from point A to point B। और अगर डेफिनेशन में लिख रहे हो तो राइट from one point to the other, ठीक है, from one point to the other. This is going to be potential difference between A and B, potential difference between 2 points, okay। So to find this, simply it is VA minus VB. If they've given the potentials, if you know the potential of A, you know the potential of B, potential difference will be VA minus VB, है ना, if VA is greater। Otherwise simply just use the same formula, work upon charge, okay। Potential difference is represented by V, okay। Let me clarify here. Potential difference is represented by V. Potential is also represented by V, but that is because they're basically the same thing. It's basically VA minus VB, right? But it's still potential. It's just the potential between 2 points, so we call it potential difference. So the unit is also the same, volts. So potential difference is represented by V. The SI unit is also represented by V, okay, but know the difference, okay। This is volt and this V is potential difference, right? Now what is the point of potential difference? The point is, without potential difference current will not flow. So if I have A and B, and if I say at A the potential is V1 and at B the potential is V2, so the potential difference is V1 minus V2. But if V1 is equal to V2, है ना, if V1 is equal to V2, then V1 minus V2 is equal to 0. There is no potential difference between these 2 points, so no current will flow, Okay, remember, current will only flow if there is a potential difference across the 2 points. Okay, if 2 points have potential difference, current will flow. If they don't have a potential difference, current will not flow. Okay, and current will always go from higher potential to lower potential. Like how, if you have a cell, right? If you have a cell, you will have one end which says positive, one end which says negative, right? So this side has higher potential, this side will have lower potential. So when we make a circuit, okay, okay, forget about this for now. This is just anything. This could be a light bulb, okay, just anything in the middle, and you create a circuit with this cell, and you create a circuit with this cell. Then the current over here will flow from positive to negative. Sorry, current will flow from positive to negative. Okay, and this is how the current will flow. But if there is no potential difference, then the current will not flow. So in a cell, what happens is basically there is a chemical reaction which keeps a potential difference. The moment the potential difference becomes zero, current stops flowing, and we say, oh, the battery or the cell is out of charge. Okay, it's out of charge because no current is flowing, and no current is flowing because the potential difference is no longer there. Now we move on to resistance. Very important concept. I think it is the most important concept which is there, right? Everything they ask will be on the basis of resistance, right? Now resistance, I'm sure you all know, in ninth you must have studied, right? Resistance is the obstruction offered to the flow of current. Okay, but where does this obstruction come from? Why is there an obstruction? If there is a potential difference, current is flowing, let the current flow. Current should just flow. Why is there obstruction? Why is there some blockage? Why is something stopping it? Okay, let's discuss it in depth. Okay, let's say this is a conductor or a wire. Okay, this is my wire. Okay, very thick wire. Let's just look into the wire. इसमें क्या देखेंगे? There'll be electrons. Okay, let's say that the dot with an arrow is the electron, and these are positive particles. Okay, these are positive particles, and this is an electron. Okay, electron, and the arrow shows the movement. Okay, the arrow over here shows the movement of the electron. So initially you will see, if the wire is made of copper or any other metal, these electrons, like I mentioned earlier, are free to move. They're free to move, so they'll continue moving around, but it's all very random. Okay, their movement is completely random. So eventually what happens is, you can say that no current is flowing, even though we've said before that current is the movement of charge. These electrons are moving, so there should be current. Okay, we don't consider there to be any current because they're moving randomly, so technically all of these cancel each other out, and we don't consider it as any substantial current that is flowing. Okay, so this is what happens when the copper wire is just left. लेकिन अब हमने क्या किया, वी टुक दिस सेम वायर, ओके, वी टुक द सेम वायर एंड नाउ व्हाट वी आर डूइंग इज, हमने इसको कनेक्ट किया, ठीक है, एक सेल से। सेल को ऐसे रिप्रेजेंट करते हैं, अ लॉन्ग लाइन फॉलोड बाय स्मॉल लाइन, ठीक है, इसको ऐसे रिप्रेजेंट करते हैं। और हमने इस वायर को इससे कनेक्ट कर दिया, इस कंडक्टर को, जो भी ये कंडक्टर है, हमने इसको एक सेल से कनेक्ट कर दिया। जो लॉन्ग साइड होता है वो पॉजिटिव होता है, जो स्मॉलर साइड होता है वो नेगेटिव होता है। तो अब इस तरफ इस कंडक्टर के पॉजिटिव चार्ज आ जाएगा, कंडक्टर के इस तरफ नेगेटिव चार्ज आ जाएगा। नाउ इलेक्ट्रॉन्स क्या है, नेगेटिवली चार्ज बॉडीज़। तो सडनली ये जो सारी इलेक्ट्रॉन्स है ना, 1 सेकेंड, all these electrons which are present, all of them will start moving towards the positive charge, positive side, because they are negatively charged bodies, वो पॉजिटिव की तरफ जाएंगे। सारे ऐसे बल्क में सारे जो भी इलेक्ट्रॉन्स हैं वो बस चले जाएंगे इस डायरेक्शन में, ठीक है। और इनके बीच में ये पॉजिटिव पार्टिकल्स होती हैं, है ना। ऑल ऑफ देम विल स्टार्ट मूविंग, क्योंकि अब इन पे फोर्स एक्ट कर रहा है। ये पॉजिटिव साइड है ना, ये पॉजिटिव साइड है, इलेक्ट्रॉन्स है नेगेटिवली चार्ज, तो उन पे इलेक्ट्रोस्टैटिक फोर्स लगता है, विच इज़ द फोर्स बिटवीन टू चार्ज बॉडीज़। तो अब ये पॉजिटिव चार्ज, द नेगेटिव चार्जेस विल बी अट्रैक्टेड टू द पॉजिटिव चार्ज, इलेक्ट्रॉन्स सारे मूव करने लग जाएंगे। और यही होता है करंट, द मूवमेंट ऑफ दीज चार्जेस, ऑल ऑफ देम आर मूविंग टुवर्ड्स द पॉजिटिव साइड। लेकिन अगर लॉजिकली सोचें, वी नो दैट F इज इक्वल टू मास इंटू एक्सेलरेशन, है ना। इनके बीच में अभी एक फोर्स है, अट्रैक्टिव फोर्स, जो इन विच इज़ द रीज़न वाई इलेक्ट्रॉन्स ये पॉजिटिव साइड की तरफ जा रहे हैं, है ना। तो मतलब ये फोर्स एक्ट कर रही है एक सर्टन मास पे, तो एक्सेलरेशन भी तो हो गई। एक्सेलरेशन होगा तो मतलब है कि वेलोसिटी विल इंक्रीज, ठीक है। द वेलोसिटी ऑफ दीज इलेक्ट्रॉन्स शुड कीप इंक्रीजिंग, है ना। तो मतलब ये इनकी जो स्पीड है वो बढ़ती जाएगी, बढ़ती जाएगी, बढ़ती जाएगी, बढ़ती जाएगी, एंड इट विल जस्ट कीप इंक्रीजिंग, इट विल नेवर एंड, है ना। बट दैट इज़ नॉट द केस, दैट इज़ नॉट द केस, क्योंकि क्या होता है, ऑल ऑफ दीज इलेक्ट्रॉन्स जैसे ये जाते हैं एक डायरेक्शन में, ये पॉजिटिव आयंस, तो ये पॉजिटिव आयंस, पॉजिटिव पार्टिकल्स तो फिक्स्ड है, ये अपने जगह पर फिक्स्ड है। तो जब ये इलेक्ट्रॉन्स हिलते हैं, दे विल कोलाइड विद दीज पॉजिटिव पार्टिकल्स, है ना। इनसे कोलाइड करके अब ये वाला इलेक्ट्रॉन ऐसे कोलाइड करके फिर इधर आ जाएगा, ये वाला, और फिर ये वाला इससे कोलाइड करके इधर आ जाएगा, ये वाला इससे कोलाइड करके इधर आ जाएगा, है ना। तो जैसी जैसी इनकी स्पीड बढ़ती जाती है ना, फोर्स की वजह से जैसी जैसे एक्सेलरेशन होता है वैसे इनका कोलिजन हो जाता है। कोलिजन की वजह से क्या हुआ, इनकी पोजीशन हिंडर हो गई, स्पीड कम हो गई, है ना, इनकी स्पीड कम हो गई बिकॉज ऑफ दिस कोलिजन, ठीक है। अब हम ये क्वेश्चन पूछते हैं, okay, listen very carefully. When the force of attraction acts on the electrons, causing them to move towards the positive potential, है ना। When the force of attraction acts on the electrons, causing them to move towards the positive potential, they acquire kinetic energy, है ना, क्योंकि अब इनमें एक्सेलरेशन आ गई है, वेलोसिटी आ गई है ना, एक्सेलरेशन हो गई तो रेस्ट से दे स्टार्ट मूविंग इन वन डायरेक्शन, सो दे एक्वायर सम वेलोसिटी, कुछ वेलोसिटी तो मिल गई इनको, एंड बिकॉज ऑफ दिस वेलोसिटी वी कैन से कि उनमें काइनेटिक एनर्जी है, सो दे एक्वायर काइनेटिक एनर्जी। लेकिन अब हमें पता है कि ये तो कोलाइड करेंगे, इफ collisions take place and produce resistance, the speed of electrons are reduced। ठीक है, इनकी जो स्पीड्स हैं वो कोलिजन के बाद इनकी पोजीशन चेंज हो जाती है और इनकी स्पीड भी कम हो जाती है ना, ठीक है, बिकॉज वो सारे इलेक्ट्रॉन्स इस डायरेक्शन में मूव कर रहे हैं। अब लेकिन इन्होंने कोलाइड कर दिया इनके साथ, कोलाइडेड विद द पॉजिटिव पार्टिकल, तो अब इसकी जो स्पीड थी वो ऑब्वियसली कम हो गई। सो द स्पीड ऑफ इलेक्ट्रॉन्स, द स्पीड्स ऑफ इलेक्ट्रॉन्स आर रिड्यूस। हर इलेक्ट्रॉन की जो स्पीड है वो कम हो जाती है। नाउ वी नो काइनेटिक एनर्जी इज इक्वल टू हाफ mv², है ना, दिस इज काइनेटिक एनर्जी। तो अगर वेलोसिटी कम हो रही है तो काइनेटिक एनर्जी कम होगी, काइनेटिक एनर्जी भी कम होगी। बट नाउ द क्वेश्चन कम्स, काइनेटिक एनर्जी कम हुई, वी नो दैट, we know from the law of conservation of energy that energy can neither be created nor destroyed। तो जब ये काइनेटिक एनर्जी कम हो रही है, हर इलेक्ट्रॉन की कम हो रही है, सो what happens to the kinetic energy? थिंक अबाउट इट फॉर अ सेकेंड, व्हाट हैपन्स टू द एनर्जी, है ना, जो इलेक्ट्रॉन्स की काइनेटिक एनर्जी वो तो चली गई, बिकॉज द स्पीड इज गेटिंग रिड्यूस्ड बिकॉज ऑफ द कोलिजन्स। सो व्हाट हैपन्स टू दिस एनर्जी? दिस एनर्जी गेट्स कन्वर्टेड into heat energy। This kinetic energy gets converted into heat energy। So अब इसमें से उल्टा क्वेश्चन भी आ सकता है, what is the cause of heat being produced in the conductor? And you will say the collisions or the resistance, the resistance which is caused by the collisions of electrons and the positive particles and the electrons themselves। ठीक है, कभी कभार ये electrons अपने आप में कोलाइड हो जाते हैं, है ना। So because of these collisions there is resistance which causes a loss of kinetic energy of the electrons, and this gets converted into heat energy, so the conductor gets heated up। This is the explanation of what resistance is। ठीक है, और last thing is current will in totality still flow। ठीक है, ऐसा नहीं है कि इलेक्ट्रॉन अब ये कोलाइड हो गया, कोलाइड होके अब यहाँ पे आ गया मेरा इलेक्ट्रॉन तो बस सब खत्म, दिस इज़ न्यूट्रलाइज्ड। नो, इस इलेक्ट्रॉन में अभी भी नेगेटिव चार्ज है ना, अब ये वापस जाके पॉजिटिव की तरफ जाएगा, दिस विल अगेन मूव टुवर्ड्स द पॉजिटिव एंड। ठीक है, सो दैट इज़ वाई करंट विल स्टिल फ्लो बट द स्पीड ऑफ इलेक्ट्रॉन्स डज नॉट इंक्रीज, है ना, it is only reduced where there are obstructions, and the obstructions or the obstruction is called resistance। ठीक है, now we come to Ohm's law। ठीक है, Ohm's law में हमें एक रिलेशन मिलती है। If I say that between these 2 points A and B, है ना, there is a current I flowing, okay, from A to B, we can say that there is a potential difference AB. There is a potential difference between A and B, which is VAB, and we know A will be positive and B will be negative. क्या हमने बोला था? Electrons will always go from negative to positive because electrons are negatively charged, they will go towards the positive end, है ना? But current is always in a direction opposite to the flow of electrons, so current will go from positive to negative. ठीक है? Now हमें ये पोटेंशियल डिफरेंस और ये करंट के बीच में रिलेशन मिलती है. लाइक वी विल से इफ पोटेंशियल डिफरेंस बिटवीन दीज इज 5 volts, ठीक है, देन लेट्स से करंट I इज इक्वल टू 3 एम्पियर. ओके, अब ओम ने क्या नोटिस किया? 1 second. ठीक है, अब ओम what Ohm noticed is that if I double this potential difference, अगर अब A और B का potential difference 5 नहीं लेकिन 5 into 2 कर दिया which is 10 volt, ठीक है, then suddenly this current becomes 6 ampere. अगर इसको मैंने एक और बार डबल किया, that is I made this 20 volt, तो ये बन गया 12 एम्पियर. इसको 60 वोल्ट बनाया तो ये 36 एम्पियर बन गया. एंड दिस वाज ओम्स लॉ. ओम्स लॉ नाउ स्टेट्स दैट द करंट flowing in a conductor is directly proportional to the potential difference applied across its ends. Okay, provided that the physical qualities and temperature of the conductor are constant. ठीक है, don't remember this last part, it's very important. Physical qualities and temperature of the conductor remain constant. ठीक है, so current flowing in a conductor is directly proportional to the potential difference applied across its ends. जैसे हम यहाँ देख सकते हैं I is directly proportional to V, है ना, IAB over here is directly proportional to VAB. so this means that if अगर हमने पोटेंशियल डिफरेंस को डबल किया तो यहाँ का करंट भी डबल हो जाएगा, है ना. पोटेंशियल को आधा किया तो करंट भी आधा हो जाएगा. दैट्स हाउ डायरेक्ट प्रोपोर्शनैलिटी वर्क्स. बट नाउ व्हाट वी कैन से इज सिंस I is directly proportional to V, okay, then V upon I will always be a constant. ठीक है, is always equal to a constant. जहाँ पर भी देखूँ अगर मैं वोल्टेज को करंट से डिवाइड करूँगा I will get a constant. और इसका सिंपल लॉजिक ये है कि अगर मैं वोल्टेज को 2 वोल्ट रखूँगा, ओके, इफ़ आई मेक दिस 2 volts, then बिकॉज ये दोनों डायरेक्टली प्रोपोर्शनल है, ये बन जाएगा 2i, है ना। तो ये कट के वापस vi बन जाएगा। अगर मैं वोल्टेज को हाफ करूँ, ठीक है, तो v/2 करंट भी आधा हो जाएगा, तो i/2, है ना। ये ऊपर जाएगा, ये नीचे आएगा, है ना, ये कट जाएगा फिर, सो v/i वापस मिल गया। तो हम जो भी करें हमें वापस v/i की वैल्यू आएगी। दैट्स वाई दिस v/i इज़ अ कांस्टेंट, ठीक है। एंड दिस यू कैन सी विद एनी प्रोपोर्शनैलिटी, ओके। इफ टू थिंग्स आर डायरेक्टली प्रोपोर्शनल देन one upon the other will always be a constant, ठीक है। So v/i is equal to a constant, and we say that this constant is equal to the resistance. This constant is equal to the resistance. तो अगर ये मेरा वायर है, you have current AB, you have VAB. Now let's say this इस वायर के अंदर, like we saw earlier, हर वायर के अंदर पॉजिटिव पार्टिकल्स होते हैं, इसलिए कोलिजन्स होते हैं। तो हर वायर का अपना एक रेजिस्टेंस होता है, तो रेजिस्टेंस AB, ओके, दिस इज द रेजिस्टेंस ऑफ द वायर। अब इफ वी हैव v/i is equal to r, then we can say that v is equal to IR, where v is potential difference, I is current, and R is resistance. And this is known as equation of Ohm's law. This is equation of Ohm's law, ठीक है। Thus the resistance of a conductor, जो ये resistance है, जितना भी रेजिस्टेंस है, इट इज़ इक्वल टू द पोटेंशियल डिफरेंस ऑफ द कंडक्टर अपॉन द करंट फ्लोइंग थ्रू द कंडक्टर। तो इससे हम आर का एसआई यूनिट निकाल सकते हैं। एसआई यूनिट ऑफ आर विल बी एसआई यूनिट ऑफ पोटेंशियल डिफरेंस विच इज़ वी अपॉन पोटेंशियल डिफरेंस ऑफ करंट विच इज़ ए एम्पियर एंड वोल्ट, है ना। तो एसआई यूनिट ऑफ R is equal to V/A, VA minus 1, and we call this ohm, ठीक है, and we are represented as this, ठीक है। ये इसका representation है, ohm, named after the scientist who made Ohm's law. Resistance is represented by this symbol, okay, simple, just draw a line, make a hoop like this, okay, this is the symbol of resistance. Okay, now we have another small concept which is conductance, ठीक है। Conductance simply means the ability of the current to flow, ठीक है, the ability of the current to flow. Resistance was the obstruction, so how much of the current is not able to flow or how much of the current is being stopped, and conductance will be the opposite. So conductance is equal to 1 upon R, 1 upon resistance. Conductance is simply 1 upon resistance, so SI unit of conductance is ohm minus 1, ठीक है, ohm minus 1. Now there are two types of resistors, ठीक है। A resistor is anything which provides resistance, very simply. Resistor is something which provides resistance. Now okay, before we move on to ohmic and non-ohmic resistors, you have to know another theoretical concept which is not very different. Limitation of Ohm's law. Try to think, what is the limitation of Ohm's law? What is one condition of Ohm's law that stops it from being universal? Okay, if I just make a statement and I say Ohm's law is not universal, ये हर केस हर सिनेरियो में अप्लाई नहीं हो सकता, okay, then what could be the limitation? Look at the definition once. Provided that the physical qualities and temperature of the conductor are constant. ठीक है, physical qualities and temperature of the conductor are constant. और हमने ऊपर पढ़ा था रेजिस्टेंस में कि हीट तो बनती है, जब भी रेजिस्टेंस होगा हीट होगी. So where there is resistance there is heat, and if there is heat the temperature will change. If the temperature will change, Ohm's law will not be applicable. So the limitation of Ohm's law is that temperature must be constant. ठीक है. Now ohmic and non-ohmic resistors, very simple. Resistor something which provides resistance. Ohmic resistor, ठीक है, simply follows Ohm's law, okay, and non-ohmic does not follow Ohm's law, okay. Ohmic के एग्जाम्पल्स हैं मेटालिक कंडक्टर्स, ठीक है, जैसे कॉपर, गोल्ड, सिल्वर, एल्युमिनियम. These are your metallic conductors. These will always follow Ohm's law. Aside from this, you have nichrome. Okay, we'll talk about this in a little bit. You will have copper sulfate solution. Okay, this is a solution. This is an electrolyte. You will study about this in chemistry, but just know this also follows Ohm's law, okay. But then again, all of these will follow Ohm's law under a constant temperature, okay. Temperature must be constant. But non-ohmic resistors do not follow Ohm's law even if temperature is constant. Even if temperature is constant, we will find that current is not directly proportional to the potential difference. And examples for this are LED, okay, LED, solar cells, junction diode, ठीक है, transistor and filament of a bulb, ठीक है. You should just know a couple of examples. Ohmic resistors are also known as linear resistors, and these are known as non-linear resistors. But why? Linear means line, straight line, okay. Linear means a straight line, non-linear means not in a straight line. So why do we say that ohmic resistors are linear whereas non-ohmic resistors are non-linear? We do this by creating a graph, okay. In this graph I will say that the y-axis is voltage and the x-axis is current. Now for an ohmic resistor, you will find that when you plot the points, okay. Now let's say for a certain ohmic resistor I applied a potential difference of 4 volts and I found out that the current is 2 ampere. Then I applied a voltage of 6 volts and I got a current of 3 ampere. Then I applied, oh sorry, what am I doing? If you apply a potential difference of 4, the current is 2 ampere, so the point on the graph will be somewhere here. 6 and 3, the point will be somewhere over here. For 8 and 4, the point will be somewhere over here. And even up till 100 volts over here, I will get 50. Okay, this is what I found out, and this point will be somewhere over here. Okay, now I'll find that sorry, this is not a good example, right? I will find that this line will always be a straight line which will pass through the origin of the graph. Origin of the graph is 0, 0, right? And this will always be a straight line. For an ohmic resistor, this will always be a straight line, whereas for a non-ohmic resistor, my VI graph will look something like this. It will be a curve. Okay, and this curve may pass through the origin like this one, or the VI graph of a non-ohmic resistor might not even pass through the origin. Okay, it's not necessary. So this is why ohmic resistors are always known as linear, because the graph is straight line. It's a straight line and it passes through origin. Okay, for non-ohmic, always a curve, not a straight line, and does not and it may not pass through origin. Okay, it may not pass through the origin. Now let us try to find out the resistance from this ohmic graph. We know that the resistance is, we can get resistance by V is equal to IR, so R is equal to V upon I. But how will we get it from this graph? Let's take a look at this graph carefully. Let us try to find the slope of this graph. Okay, the slope of this graph is always y2 minus y1 upon x2 minus x1. This is the formula of a slope, है ना? So if you take 2 points, the y of the second point minus the y of the first point upon the x of the second point minus the x of the first point, है ना? So for this slope, let's say I take this point 100, 100 comma 50. This point is 50 comma 100. You write the x-axis value first. This is 50 comma 100, and this is, and let's take this point 4 comma 8. Okay, so now I will take, you following the formula, 100 minus 8 upon 50 minus 4, which is equal to 92 upon 46, which is equal to 2. But now we know that this is the same as doing V upon I, right? Because our y-axis, our y values are all voltage and x-axis is always current, right, in a VI graph. So this is 2 ohms. The slope of the graph, the slope of a VI graph will always give you the resistance. Always you'll get a resistance on the slope of a VI graph. Okay. Now, how they trick you is, sometimes they'll give you a graph and they'll say find the resistance, but what they'll do is they'll make this an IV graph instead of a VI graph. So for this you will have to find the slope and then you'll have to reciprocate it. So here R is equal to 1 upon slope of IV graph. Okay, 1 upon slope of the IV graph, that is a resistance. Now they might also ask you to find the resistance for a non-ohmic resistor, but for this the resistance won't be constant. Okay, we know that if it follows Ohm's law, resistance will be a constant, which is V upon I, है ना, and V is directly proportional to I. So here from the ohmic graph we can see that V is always directly proportional to I. When it's 2, when this is 4, this is 2, if it gets doubled, this becomes 8, this becomes 4. Okay, so they're directly proportional. And now no matter which 2 points you take, because it's a straight line, the slope will always be the same. So no matter which 2 points you take, you will always get the resistance as 2 ohms. Okay, for this ohmic resistor. But for a non-ohmic resistor, they might give you anything random. They might say that this point, okay, they might say at this point of the curve the potential difference is 10 and the current is 3. So find the resistance at this point, which will be 10 upon 3, which is 3.33. okay, ohm, 3.33 ohm. Okay, that's what they might do. They might give you a non-ohmic resistor and then give you an IV graph. These are just how they trick you. Now we move on to the factors affecting resistance. We will be discussing 4 factors. Okay, first one is going to be material. Okay, when it comes to material, if we talk about just conductors in general, if a material has free electrons, then it is a conductor. It will be able to conduct electricity. Why? Because if the electrons are free, the electrons can move. And what is current? Current is the motion of a charge. Current is a charge in motion, है ना. तो अगर इलेक्ट्रॉन्स फ्री होंगे, हिल पाएंगे, फिर हमारा करंट होगा. तो इस मटेरियल से करंट बनेगा, एंड दैट इज़ वाई इट इज़ अ कंडक्टर. लेकिन अगर मटेरियल में फिक्स्ड इलेक्ट्रॉन्स हैं, अगर इलेक्ट्रॉन्स हिल ही नहीं सकती, तो नो करंट, है ना. नो करंट मतलब ये इंसुलेटर और नॉन कंडक्टर. इट इज़ एन इंसुलेटर और इट इज़ अ नॉन कंडक्टर. ठीक है, जैसे इसमें आते हैं हमारे मेटल्स और इसमें आते हैं समथिंग लाइक वुड, रबर. ठीक है, सो दिस इज़ हाउ इट डिपेंड्स ऑन द on whether it has free electrons or not. Even within metals now, if something has more free electrons, है ना, something has more free electrons, then it will have more current. क्यों? Because I is equal to Q upon T. अगर ज़्यादा electrons हैं, Ne upon T, है ना, तो अगर ज़्यादा number of electrons है, ज़्यादा चार्ज होगी तो करंट ज़्यादा होगी, है ना. सिंपल लॉजिक. और अगर ज़्यादा करंट है तो फिर ये बेटर कंडक्टर हुआ, क्योंकि इससे ज़्यादा करंट जा सकता है. ओके, दैट इज़ वाई इट इज़ अ गुड कंडक्टर. ठीक है. Now moving on, the second factor is length of the conductor. ठीक है. Now think about this logically. If I have this conductor, again these are my electrons. ठीक है. ठीक है, इनके बीच में पॉजिटिव पार्टिकल्स होंगे मान लो. ठीक है, यहाँ पे पॉजिटिव है, यहाँ पे नेगेटिव है, तो ये सारे इस डायरेक्शन में आ जाएंगे, है ना. ऑल ऑफ दीज विल स्टार्ट मूविंग टुवर्ड्स द पॉजिटिव साइड. और जब ये पॉजिटिव साइड की तरफ मूव करेंगे फिर क्या होगा, कोलिजन्स होंगी, रेजिस्टेंस बनेगा, है ना. सो नाउ इमेजिन इफ़ आई हैव अ लॉन्गर कंडक्टर. ठीक है, अगर सेम मटेरियल का हो और इसका कंडक्टर ज़्यादा लंबा है तो फिर these electrons overall they will have to cover a longer distance. अगर पॉजिटिव यहाँ पे है, इनको क्या करना है, इनको पॉजिटिव तक पहुँचना है ना. ये छोटा कंडक्टर है, ये तो पहुँच जाएंगे, लेकिन ये ज़्यादा लंबा कंडक्टर है तो उनको लंबी दूरी तक जाना पड़ेगा. दे हैव टू कवर मोर डिस्टेंस, और इस लंबे डिस्टेंस में ज़्यादा कोलिजन्स होंगे, ज़्यादा पार्टिकल्स होंगे, है ना, क्योंकि हर मटेरियल में कॉन्सेंट्रेशन ऑफ फ्री इलेक्ट्रॉन सेम होता है. हर मटेरियल में कॉन्सेंट्रेशन ऑफ फ्री इलेक्ट्रॉन्स सेम होता है. ठीक है, तो जितना ज़्यादा होगा उतने ज़्यादा पॉजिटिव पार्टिकल्स होंगे, है ना. तो ये सारे इलेक्ट्रॉन्स और कोलाइड करेंगे, और कोलाइड करेंगे तो रेजिस्टेंस बढ़ जाएगी. सो वी कैन से दैट रेजिस्टेंस इंक्रीजेज विद द लेंथ ऑफ द कंडक्टर, and we find that R is directly proportional to L, where L is length of conductor. ठीक है, ठीक है, R is directly proportional to L. तो अगर originally R is 2 ohm, ठीक है, and L is 5 meters, if L is 10 meters for the same conductor, for the same material, then R will be equal to 4 ohm. ठीक है. अब इसके बाद थोड़ी स्पेस की कमी है. इट डिपेंड्स ऑन द थिकनेस ऑफ कंडक्टर. थिकनेस कैसे डिटर्मिन होगा? थिकनेस डिटर्मिन होगा एरिया ऑफ क्रॉस सेक्शन से, है ना. ठीक है, ये जो सर्कल के एंडिंग्स हैं, ये जो सर्कल के ओपनिंग्स हैं, ठीक है, इनका जो सर्कल है इनमें जितना ज़्यादा एरिया होगा उतना ज़्यादा थिक होगा हमारा वायर, है ना. सो द थिकनेस ऑफ द कंडक्टर इज़ डिपेंडेंट ऑन द एरिया ऑफ क्रॉस सेक्शन. ठीक है, बट इन जनरल अगर हम देखें, जैसे ये डायग्राम है, ठीक है, अगर हम इन दोनों को माने एंड लेट्स जस्ट से इंस्टेड ऑफ लेंथ चेंज होने में अगर हम बोलें कि एक ऐसा है और दूसरा, ठीक है, और दूसरा ऐसा है, ठीक है, इनकी लेंथ सेम है, ठीक है, दोनों की लेंथ L, ठीक है, दोनों की लेंथ है L, दोनों की लेंथ सेम है. अब इसमें जो पार्टिकल्स होंगे, ठीक है, इलेक्ट्रॉन्स, वो पॉजिटिव की तरफ जाएंगे, है ना. अब इफ़ यू थिंक अबाउट इट, ये जो ज़्यादा थिक वाला है ना, इसमें इलेक्ट्रॉन्स के पास ज़्यादा एरिया ऑफ क्रॉस सेक्शन है. ये सर्कल का एरिया ज़्यादा बड़ा है, ज़्यादा स्पेस है जाने के लिए, है ना. और अगर ज़्यादा स्पेस है जाने के लिए तो फिर ये कम टाइम में पहुंच पाएंगे. कम टाइम में पहुंच पाएंगे तो फिर करंट बढ़ जाएगी. तो फिर अगर करंट बढ़ रही है फिर रेजिस्टेंस कम हो जाएगी, है ना, क्योंकि रेजिस्टेंस कम है तभी तो करंट ज़्यादा जा रही है, अगर रेजिस्टेंस ज़्यादा होती तो करंट कम जाती. सो इन अ थिकर कंडक्टर more current will be able to flow, more current is able to flow, which means that the resistance is less. इसको हम ऐसे भी कह सकते हैं V is equal to IR, है ना. तो अगर हम V को कांस्टेंट रखें, है ना, अगर हम बोले V को कांस्टेंट रखो, then we can say that I is inversely proportional to R, है ना. तो अगर ज़्यादा करंट फ्लो कर रहा है उसका मतलब है कि रेजिस्टेंस कम है इस कंडक्टर का. सो वी फाइंड आउट that R is inversely proportional to area of cross section. Area of cross section is area of this circle, है ना. ये जो circle है which is the area of cross section of the wire, R is inversely proportional to that. So resistance is inversely proportional to 1 upon pi R square, pi R square, which is the formula of area for a circle. ठीक है, ये 3 फैक्टर्स हो गए. फोर्थ फैक्टर है हमारा टेम्परेचर. अब इसमें सिंपल सा कॉन्सेप्ट लगता है. इफ़ टेम्परेचर इंक्रीजेस देन काइनेटिक एनर्जी इंक्रीजेस, है ना. तो मतलब अगर हमने कंडक्टर की टेम्परेचर बढ़ा दी, इलेक्ट्रॉन्स में ज़्यादा काइनेटिक एनर्जी आ जाएगी एंड द इलेक्ट्रॉन्स विल स्टार्ट टू मूव एंड दे विल स्टार्ट टू मूव मोर विगरसली बिकॉज दे हैव मोर एनर्जी, है ना. लेकिन ये इतनी ज़्यादा एनर्जी से मूव करते हैं तो इनकी कोलिजन भी ज़्यादा हो जाती है ना. द नंबर ऑफ कोलिजन्स इंक्रीजेज क्योंकि ये इतनी एनर्जी से जा रही है, ठीक है. और जो इनका रैंडम मोशन होता है ना, लाइक आई सेड व्हेन देयर इज़ नो पोटेंशियल डिफरेंस अप्लाइड, ये इलेक्ट्रॉन्स का रैंडम मोशन होता है. इलेक्ट्रॉन्स का रैंडम मोशन में व्हाट हैपेंस इज बिकॉज the temperature is increasing, the kinetic energy is increasing, so the random motion increases, and as the random motion increases the collisions increase. तो उसी से it starts losing that energy, उसी से resistance बढ़ती जाती है ना. So the increase of temperature also implies the increase of resistance, है ना. We won't say that it is directly proportional, but if the temperature increases then the resistance increases. So based on this, now they can ask you a lot of questions based on these, right, which I will discuss towards the end. I'll give you a couple of questions to solve. Okay, right now let's move on to specific resistance or resistivity, है ना. Right now whatever we've discussed, if we put it together, okay, we discovered that R is directly proportional to L and R is inversely proportional to area of cross section. So we can say that R is directly proportional to length upon area of cross section, है ना. अगर R को डबल करेंगे तो L डबल हो जाएगी और एरिया हाफ हो जाएगी. So this will keep the same thing anyway. So this is the same. Now again, like I said, if we reverse this, right, we can say that R A upon L is equal to a constant. जैसे हमने V is equal to IR में किया था, है ना. V is equal to IR कैसे आया? V is proportional to I, so V upon I is constant, है ना. तो यहाँ पे भी इसको उल्टा करके इस तरफ लेके R A upon L is equal to a constant. अब इस constant को क्या कहते हैं हम? रो, ठीक है. ये इसका सिंबल है रो एंड दिस इज नोन एज स्पेसिफिक रेजिस्टेंस और रेजिस्टिविटी. दिस इज स्पेसिफिक रेजिस्टेंस और रेजिस्टिविटी एंड specific resistance is constant for a certain material, ठीक है. तो हमें क्या मिलता है? R into area of cross section upon the length of the conductor is equal to specific resistivity, and इससे we also get the formula of resistance. Resistance is equal to rho into length of the conductor upon area of the cross section of the conductor. ठीक है? And rho is constant for a certain material. Specific resistivity आप देखोगे तो होता क्या है? It is the resistivity of a certain material for unit length and unit area of cross section. ठीक है, हमने फिगर आउट किया कि आर ए अपॉन एल तो कांस्टेंट है ही. ठीक है, वी फिगर्ड आउट कि ये तो कांस्टेंट है ही. फिर एक्सपेरिमेंटेशन करके हमें पता चला दैट ऑल ऑफ दिस इज डिफरेंट फॉर डिफरेंट मटेरियल्स. हालांकि this condition is true, okay, for all conductors. And now what I do is, if I take a copper conductor for example, I will keep testing this. I will change the length, I will change the area of cross section, compare it with the resistance, and try to find out what is the value of this constant. Okay, and after I found out the value of this constant, okay, by dividing whatever value of resistance I got upon resistance I got into A by L. ठीक है, I used this multiple times to try to find the constant, and I got a value rho. I got this constant value, but now I tried the same value with an iron conductor, but it wasn't there, it wasn't working, sorry. So then we discovered that rho is constant only for a certain material. So every material has a different specific resistance, है ना. लेकिन the same material, two conductors of the same material will always have the same specific resistance. Okay, so if I have two copper conductors, है ना, two copper conductors, this is of length 2 meters, this has an area of cross section of 4 meter square, and now I have another conductor of copper. Okay, this is copper, this is copper, and I say this one has a length of 2 meters and an area of cross section of 2 meter square. Compare R1, which is the resistance of this, and R2, which is the resistance of this, and also compare rho 1, which is the specific resistance of this, and rho 2, which is the specific resistance of this. So now for R1 upon R2, you will see, you'll plug in the formula, है ना. R is equal to rho L by A, rho L1 by A1, है ना, upon rho L2 by A2. So we know that rho for a certain material is the same, so rho we can cancel out. Rest you have L1, which is 2 meters, upon 4 meter square, which is the area of cross section of the first conductor, and then you have L2, which is also 2 meters, है ना, but this has an area of cross section of 2 meter square. Cut this, cut this, cut this, you left with 1 upon 2. So the ratio of R1 to R2 is 1:2. But now if we have to compare rho 1 and rho 2, है ना, we'll plug in the formula here now. Rho 1 is equal to R1 into A1 upon L1 upon, using this formula over here, R2 into A2 upon L2, which is equal to, now we know R1 upon R2 is equal to 1 upon 2, है ना. So R1 upon R2 is equal to 1 upon 2, so 1 into A1, which is 4 upon 2 upon R1 upon R2 was 2, so 2 over here multiplied by area of cross section 2, which is 2, upon L2, which is 2. Okay, so now we can cut this with this, and we get 4 upon 4, these two will get multiplied. These two will get multiplied. So we get 4 upon 4, which is equal to 1. And row 1 is to row 2 is equal to 1 is to 1. So this is how we've also proved that for the same conductor we're getting 1 is to 1 as the ratio of specific resistances, है ना? So just remember that the specific resistance of the same conductor, of the same material is always the same, no matter the length or the area of the conductor. But there are factors which the specific resistance depends on, है ना? First is obviously material, because like we discussed, it's different for every material. You have 3 different types of materials or 4 different types of materials we'll take conductors, we'll take metals, alloys, semiconductors and insulators. Okay, these aren't that important. Just know metals have very low specific resistance, alloys will have low specific resistance, है ना? Alloys also have very low specific resistance usually. Metals and alloys both usually have very low specific resistance. Semiconductors will have low resistances, okay, low, not as low as metals and alloys, but a low specific resistance. And insulators will have high specific resistance. Okay, so now if you think about it, since metals have a very low specific resistance, okay, if I take R1 L upon A as the resistance of a metal, and then I take R2 is equal to rho 2 L upon A as the resistance of this insulator. Okay, now L upon A, if we take these to be same length and same area, okay, if we take this as the same length as the same area, right? But we know that rho 2, which is specific resistance of the insulator, is greater than rho 1, then obviously the resistance of the insulator will be greater than the resistance of the metal. Next thing which specific resistance depends on is temperature. This is very important because this came in the physics board paper as well for this year, and they tested this very sneakily. We know that the rho or specific resistance for the same material is constant, but it changes with temperature. Okay, rho for the same material is constant, but it changes with temperature. Now this again depends on the material. So for metals, usually if temperature increases, then the specific resistance increases, okay, for metals. Then if temperature increases, rho decreases for semiconductors. And for certain alloys, it doesn't depend on temperature. Certain alloys like constant tan and manganin do not change with temperature. Okay, rho of alloys like constant tan and manganin do not change with temperature. Okay, now we talk about, oh sorry, we missed out on the unit of specific resistivity, है ना? We can take that out very quickly. Here we know that rho is equal to resistance into area upon length, okay, which is equal to ohm into area is meter square upon meter. This gets cut, so we get ohm meter. Okay, this is the unit of specific resistance. Okay, now the opposite, sorry, of specific resistance. Now we have another topic. Just like we had conductance, we also have where we also have conductivity, which is equal to 1 upon rho. Okay, just like we had conductance as the opposite of resistance, we have conductivity, which is the opposite of resistivity, which is specific resistance, right? So this is going to be 1 upon ohm meter. This is going to be the unit, right? Now there are some special materials which we use for certain wires, starting with wires for electrical transmission. Electrical transmission means like how current is brought to your house for your usage. Household current is brought, right? Now for these, current is generated, and now after being generated, current has to come to our house. It's a long distance that it has to travel, so we want as much current as possible to come to our house, right? Obviously, अब बिकॉज हमें ज़्यादा करंट चाहिए, हमें रेजिस्टेंस कम चाहिए होगा, सो दैट्स वाई फॉर वायर्स फॉर इलेक्ट्रिकल ट्रांसमिशन वी यूज़ metals like copper, aluminium. Okay, silver has the least specific resistance, but because it is quite expensive, most of the wires you see around you will be made of copper, right? Now these wires which are used for electrical transmission, they are made thicker. They are also made thicker to further reduce resistance, है ना? Because the thicker the wire is, the less the resistance, so they make it even thicker so that the resistance is less. And this will also, and because resistance is less, it will reduce loss of energy as heat. Resistance कम है, which means collisions कम है. Collisions कम है तो जो loss of energy होता है ना heat के form में, वो भी कम हो जाता है, and more current will be able to reach our houses. इसके बाद आता है resistance wires. ठीक है, resistance wires और standard resistors, इनका purpose ही है to provide a resistance. Their purpose is to provide a certain amount of resistance, but this resistance has to be the same, which is why we use alloys. Like constant tan and manganese, which do not depend on temperature. Usually क्या होता है, while the current is flowing, okay, as the current is flowing, the resistance produces heat, so the longer the current flows, more and more heat keeps getting produced. That's why if you want a standard resistance, you use constant tan and manganese, so that even over time the resistance does not change. Even though the temperature will change, the resistance will not change. Okay, now you have a fuse wire. This is the wire used in a fuse. You will learn more about this in the next chapter, household circuits. This is made from an alloy of lead and tin. Alloy of lead and tin, and I will explain this in the chapter of household circuits. You have filament of electric bulb. Filament of electric bulb. Filament of electric bulb is made out of tungsten. Tungsten has a high melting point. High melting point. How the filament works is, when you pass current through the light bulb, the filament starts to heat up. So the tungsten starts to heat, and because of this heat, the tungsten starts to glow. And this is how the electric bulb will give us light, because the tungsten will start to glow because of the heat. But now tungsten has a high melting point, so it will continue to glow instead of just melting. Then lastly you have heating element. Okay, heating element is used for your heater toaster oven. And we use a nichrome wire because it has high specific resistance and R increases greatly with temperature. Okay, these are things that you have to remember. Last concept is superconductor. Superconductor basically means resistance is near zero. Okay, resistance is almost zero, and this only happens in certain conductors at very low temperatures around absolute zero, which is 0 Kelvin. Okay, so 0 Kelvin, it is near these temperatures, which is a very low temperature, which is why these superconductors do not have very practical application. But you need to know the examples. You have mercury below 4.2 Kelvin, lead below 7.25 Kelvin. Okay, so below these temperatures they have a resistance which is nearing zero. And last one you need to know is niobium below 9.2 Kelvin. Now the speciality of this is, because there are no collisions, and what happens is there are no collisions, so I will apply a potential and the electrons will start moving in this direction. They'll start flowing through the circuit, through the conductor. But now the same conductor, after they start moving, even if I remove these, so now in this conductor, after I've put this positive and negative charge across its ends, I will remove these, and still the electrons will continue moving. Because of Newton's first law, an object in motion will stay in motion in the same direction unless an external force is applied on it. And now because the resistance is zero, there is no collision and there is no charge across the ends. If I put a potential across here, force will act, they will continue accelerating without any collisions. But if I don't have any potential across its ends, then it will continue moving at a constant speed. And with that, we close current electricity part A, and I will give a few questions for you to think about. Okay, starting with this. Okay, this is a VI graph of a certain conductor. Okay, this is the VI graph of a certain conductor, and now we record two different lines. Okay, one line is like this and one line is like this. Now this is resistance A, this is resistance B, है ना, because if we take out the slope of these lines we'll get resistance, so this will have resistance A and resistance B. Now resistance A has a temperature of T1 and resistance B is at a temperature of T2. This is the same conductor, so same conductor, exact same conductor, everything is same except for the temperature, right? So now you have to tell me, is T1 equal to T2, is T1 greater than T2, is T2 greater than T1, or cannot say. Okay, this is your first question. Then second question, a copper wire has a resistance R1. Okay, after stretching the same wire, to twice its length, its resistance is R2. Compare R1 to R2. Okay, now I'm going to ask you one last question. Yeah, fine. One last question I'll ask you. What was it? Last question. What can I ask? Right. I'll ask you this question. A current flows through a silver wire for some time, okay, for a certain amount of time. Now after a long time, flows through a silver wire for some time with a resistance R1. ठीक है, after a long time the resistance is measured as R2. Okay, now you have to compare R1 and R2, use greater than, less than, equal to sign, and rho 1 and rho 2. Okay, after a long time the resistance is measured as R2. Now rho 1 and rho 2, and again use greater than, less than, equal to sign. Okay, these are your questions. Thank you for watching. Stay tuned.